So the topic of today will be endpoint functions. In quantum field theory. In quantum field theory, like in quantum mechanics, of course, you are dealing with operators, with field operators. Okay? So let's denote generically an operator by phi, and I will put a hat on them to denote that they are operators. They are fields in the sense that they are a function of t and x, the space coordinate, which our notation will be to write them just a function of a single x, where this x will be t and the space x. The objects of interest for us are the ground state expectation value of these operators. These are fully interacting Heisenberg picture operators, and in order to denote that, I will put an h there as a subscript. Okay? So we are not working yet in interaction picture, and they do not satisfy linear equations. In general, in an interacting field theory, they satisfy the full nonlinear field equations. If you know these objects in a quantum field theory, then essentially if you know the collection of these objects, not just one of them, but collection for all space-time, the number of space-time points n being arbitrary, then essentially you know everything quantum field theory. You can calculate everything, including S-matrix elements from these objects. The way that you have learned to calculate S-matrix elements in quantum electrodynamics was to convert the whole problem into interaction picture and sandwich the S-matrix between an in and out state and then expanding parts of the coupling constant. Okay. But here, so there the external lines are mass shell particles. Here we are not doing that. There is no mass shell particle. There is in fact no notion of particle at this stage here. The notion of particles comes when you go to the interaction picture and write in terms of creation and annihilation operators. Here it is just some functions of space coordinates, and the expression itself, at least formally, it makes sense. It's a number of operators that if you take the matrix elements between any two vectors, you will get a function. And this is the function that we are calling the endpoint function. Now, I wrote this in the form of a scalar field, but obviously they can be spinors and vector fields, etc. So in a sort of general field theory, we will have sort of fields of various spins there. Yeah? They can also be gravitational fields for that matter, if you are dealing with quantum gravity. Whatever field theory you have, these are the objects of the most interest for us. Any questions? Good. We will see that there is a way to go directly from these objects to the S-matrix elements, for example. Okay. Now, it's very hard, if not impossible, to actually calculate them exactly. There is no non-trivial quantum field theory, or I shouldn't say non-trivial. I should say that there is no realistic quantum field theory. By realistic, I mean a quantum field theory which has been confirmed by experiments like standard model, QED, etc., in which these objects can be calculated exactly. There are some supersymmetric theories in which you can do this in 2 dimensions or in 4 dimensions, but not in non-supersymmetric theories of QED type or of the type of the standard model. So in practice, in order to get a handle on them, you have to do some approximative scheme. You have to do a perturbation theory. And that will take up a great deal of our time. We will try to make sense of these objects in perturbation theory, in which you will immediately see that they give you infinite results, and therefore we have to learn how to extract finite answers from the apparently infinite result of a calculation. Okay? Otherwise, you cannot make comparison with the experiment. The experiments never measure infinite numbers. They measure always finite numbers. But Nevertheless, despite the fact that we will spend quite a bit of time to understand them in perturbation theory, we will also try to obtain some exact results just about these functions. Not too many of them, but at least some of them. Okay? In fact, it's hard to obtain exact results about these functions unless you impose very big symmetries like supersymmetry and other things. Nevertheless, some results can be obtained. Now, to go there are various approaches. One is the operator approach or canonical quantization, which was followed in the early phase of quantum development of quantum field theory, especially by Schrödinger and others. Then there is the functional approach, functional integral approach, popularized by Feynman, and that is the most efficient way of doing it. Therefore, we will spend some time playing with the functional integrals. And this first lecture actually will start with the easiest of a functional integral, in fact, with the easiest of an integral. And then gradually we'll make progress to more complicated things. In fact, we will never calculate an integral directly. We'll just rewrite in such a way that the result that we want to obtain will come out of it. However, at least Gaussian, we should know how to calculate. Because everything eventually that we want to do in terms of functional integrals will reduce to Gaussian. Therefore, my first topic is Gaussian integral. Of course, all of you are familiar with Gaussian integral, but I will write in an unfamiliar form so that you will not be bored, hopefully. So the first thing is we will start a one-dimensional, simplest Gaussian integral. And I'm going to denote it by the symbol. Every aspect of it will be explained in a minute. Usually you write dx, but I'm going to write d phi in order that when we generalize in notation, everything is in the right place. And usually you consider a real Gaussian integral, but I'm going to consider a complex one. The integration variable is phi. I mean, let me write here the standard thing that all of you know. That's the integral that all of you know, right? Even this one you know. That if I add a term linear in x, I'm going essentially to write this object, except that I will make alpha complex and put an I in front of this. And instead of calling alpha and beta, I will call it with different names. Okay? But that's what I'm writing in the one-dimensional case. So I'm going to write that alpha as 1 plus I epsilon, where A and epsilon are both real, but epsilon is positive. And then I will add a 2j phi here. That's the beta term there. Okay? So it's exactly this object in which alpha is complex and beta is j, or I times j. And I have called this obviously the result of integration will depend both on A and j, but the part which is of interest for us is the dependence on j, not on A. You will see that the dependence on A will cancel out in the objects that we want to calculate. Okay? So the dependence on j is the important part of this integral for what we want to do. And we are going to normalize it in some way. That means we are going to consider this integral divided by the same integral in which we have set j equal to 0. This is the reason we do not need to actually evaluate any integral in practice. You will see that we can extract the j dependence without doing any integration. So this is the same object in which we have set j equal to 0. Obviously, this quantity satisfies the condition that if you set j equal to 0, it is 1 divided by 1, so therefore it should be 1. Later on, we will see that this condition is essentially the condition that the vacuum state is normalized to unity. The vacuum state of the quantum field theory is normalized to unity. That's this condition. This condition will turn out to be that. Is the notation clear? Okay. Now, in order to shorten this thing is going to be called n minus 1, and then I'll put a subscript 0. The subscript 0 here and here has been inserted because later on we will consider integrals in which the exponent is not a quadratic form like this. The exponent in the integrand, you see, is second order in phi. There's a first order term and second order term. But we will consider interesting cases will correspond, of course, to the case where you will have phi cube, phi to the 4, phi to the n, phi to the 25, whatever. Okay? So that will correspond to interacting field theory. Then we will drop this 0. So 0 always means, when the subscript 0 always means we are considering the things in which the exponent in the integrand is only a quadratic. And the name for this will be n minus 1. Therefore, I will put an n0 in front of it. This is in the denominator, so when it goes there, it becomes n0, and drop the denominator. So this denominator is going to be erased from here. Now, you know how to do this. First of all, it's too long. Let me put this condition here, sorry. That's a very important condition. It's clearly this number here, I'm going to call it D. Okay? All this strange notation is because we want to generalize it. So the condition then, first of all, the normalization condition I'm going to put here. And I'm going to continue in the next line with, let me rewrite again the simplified notation. And then you know how to do this. How do you do this integral? Complete the object in the exponent. So you write phi d phi plus 2 j phi as phi d plus j times d minus 1 d phi plus j. So if you multiply this, you will produce this term and that term, but you also will produce an extra term, which comes from the product of that, and that. And therefore, we must subtract. Okay? So we should subtract j d inverse j. If you expand everything, then the result will be the left-hand side. So therefore, there is a j dependence here and j dependence here, apparently. But when you substitute back in the integral, first of all, here there is no phi, so I can put it outside the integration and get, there is also an I over 2 here, which we should not forget, j d inverse j, then the integral remains. The claim is that this quantity here is independent of j. This integral is independent of j, despite the fact that apparently there is j dependence here. Okay? So either you have seen this before or you haven't seen it, please think about it. That this integral is independent of j. Of course, one very obvious way of seeing it is just to make a change of integration variable. We are integrating over phi, j is a constant in that integration, then it's obvious. But you can probably think of other ways of seeing it. And if it is independent of j, you can set j equal to 0, then this integral becomes the same thing as n0. Therefore, the result of the whole integral is minus I over 2 j d inverse j. With coefficient 1 here. This coefficient is 1 because n0 inverse is precisely this integral, as we have written. So let me write again here. So n0 times this quantity is 1. Now, the first generalization is to replace this single variable by an n-component vector for a finite n. So, the first generalization. Send phi to a vector, n-component vector. And the matrix D, this is both phi and j. And the matrix D, n by n matrix. Now, the notation we are going to adopt is write phi like this, j like this, and then the phi d phi plus 2j phi will become phi d phi plus 2j phi. If you choose a basis, and in any finite dimensional vector space, you can choose an orthonormal basis of then phi can be written as sum over p, phi of p times the basis vectors. And likewise for j, the bases are orthonormal. Therefore, j phi in terms of components is j of p, phi of p. And the matrix and the phi d phi will be some p q phi of p d of p q phi of q where d p q Q are the matrix elements of EP, EQ. So our integral then first of all we are integrating over n variables. So the integration measure should range over all these variables. And then in the exponent we have phi d phi plus phi j plus j phi. That's the 2 j phi term. Okay? Now, if you look at the components here, you see that this expression phi p and phi q are symmetric under the interchange of p and q. So only the symmetric part of this matrix is intact, and we will take it to be symmetric actually. Now the integral obviously, if you diagonalize d, it will be the product of n copies of what we had before, and therefore the result will be the product of n copies of what we had before. Okay? So, but still, as far as the j dependence is concerned, you do not need to evaluate the integral. All you need to do is to complete the square. Which proceeds exactly in the same way. Namely, write this as phi d plus j d inverse d phi plus j minus the extra term, which is j d inverse j. By the way, I forgot to mention that this d will always have an imaginary part. So there is an imaginary part of d which should be epsilon times the unit matrix. This I is the unit n by n unit matrix. Why do we put that there? This I epsilon. The reason is that unlike the real Gaussian, I have put a factor of I here. Okay? So when you do the Gaussian integral, normally you take its square, convert it, use the forward coordinates, and convert it into an integration over one single variable. Okay? Like x. Remember that? Now, that single variable integral can be easily integrated. It's a dx integral of alpha times x. But then when you put the boundaries, if there's an I in front of it, it will be an oscillating function. You will not know what it is. But if there's an I there, then I times I will give you -1, and it will, the integral will converge. Okay? So the reason for this I here is to make, in the one-dimensional case, the reason we put that I epsilon there is that in the one-dimensional case, you see that when you do the usual things that you do to evaluate the Gaussian integral, this will reduce to exactly the usual Gaussian integral. Okay, the same you must follow the same procedure. But this I times I gives you minus epsilon, and if epsilon is positive, exponential of minus I epsilon times x when x goes to plus or minus infinity will give 0. Okay? So therefore the integral converges. Without this term, the integral will not converge. It doesn't mean that you cannot calculate it. You can still use tricks from complex variable theory and calculate that integral. But it's more elaborate, it's more complicated than the usual tricks of ordinary Gaussian integral. It's not complicated, but you have to do some work. You have to create a counter integral to calculate it. So this is the reason why we are putting this I epsilon there. Eventually we will see that I epsilon is the I epsilon in the Feynman probability. It will descend to the I epsilon in Feynman probability. Clear why we put the I epsilon there? Okay. So this D will also have that I epsilon always. That's a very important I epsilon. I mean that small epsilon always goes to 0, but it hides plenty of information when you go to loop calculations, study the analytic properties of Feynman amplitudes after your calculation. This I epsilon will dictate to you, for example, there will be a cut in the complex plane. It will tell you whether you should go above the cut or below the cut. Okay? So it hides plenty of subtlety of quantum field theory, that I epsilon in the denominator of Feynman probabilities. These words may not make much sense to some of you or to all of you, but we will see them later on. I am just trying to emphasize the importance of that I epsilon. It should not be forgotten. So anyway, written in this form, we have isolated the J dependence, and as before, Z of J becomes exponential of minus I divided by 2, J D inverse J times N0 times integral over phi of exponential of I over 2 of this long expression, which is independent of J, as in the one-dimensional case. In other words, N0 times this object is simply 1. So this is our final result. So the result of this integral is exponential of minus I over 2 J D inverse J. Now, the second generalization. The second generalization is the infinite dimensional generalization, which is of interest for us. Again, we will consider so this is the second generalization. This is finite dimensional this is infinite dimensional. So now we are going to take this exponent to be a functional. Here you have a finite sum over P and Q of phi P dPQ phi Q. That is this expression. Instead of sum, we are going to have an integral. So we will have an integral, in fact, in the same form. We will write it again in this notation. That's the reason why I introduced in this notation. But phi will be a field. So phi is a field. And in order to bring it to the familiar form of a field that you know, I have to introduce a basis. Okay? Here I introduced the basis and I wrote this as a finite dimensional matrix and the matrix multiplication. Here also I must introduce a basis in order to write it in the familiar form of phi of x. The basis this time will be the eigenstates of the position operator x hat. So we will take x hat and assume that it is diagonal. In the Dirac notation. Okay? They are orthonormal in the Dirac notation, Dirac sense, namely, and they are complete. I am suppressing the index, the matrix index mu, etc. But it's understood that these are X has 4 components. Okay? Now the phi can be expanded in the spaces. So the expansion will be, the coefficients will be, these are the components of the vector phi in that basis. So phi of x is the inner product of x and phi. Okay? Together with x, of course, you always have also the conjugate momentum operator minus IT mu. In the basis that this object, this x, is diagonal, then p is given by this derivative operator, the very basic principle of quantum mechanics. And for operator d, I will take the infinite dimensional generalization of what we had before. So we will take d to be minus d squared. By d squared, I mean d mu. D mu. That's the meaning of d squared. Minus a constant m squared plus our friend I epsilon. And then our x d, our phi d phi will be, let me first write j phi. So the j phi, in order to find out what this is in terms of components, use the completeness relation and insert complete set of eigenvectors of x between j and phi. But then you must remember that this is what we call j phi, phi x, I'm sorry, phi x. And this we called jx. Therefore, this whole thing then is, since you are in 4 dimensions, you can also put 4 there if you like. Then it becomes j of x, phi of x. So that's what j phi stands for, this integral. Okay? Likewise, then phi d phi, we must put d for x prime, d for x, phi x prime, or phi x, x d x prime, x prime phi. This is phi x prime. This is phi x. We are dealing with the real phi. Okay? So it doesn't matter you put x here or x on the other side. And the object in between. D for x, d for x prime, phi of x, x. The operator is minus d squared minus m squared plus I epsilon times x prime times phi of x.
But why did you write d in this form?
Sorry?
Why did you write?
I just chose it. I am choosing this particular operator. Okay, for the time being, I mean, of course, this will be the kinetic energy of a real scalar field in a minute. But for time, maybe I'm just choosing the things in this way. Now, what's this? So this operator acting on the basis of x, you know how it operates in quantum mechanics. So it just comes out as a derivative operator, then x times x prime, and these are of course multiples of the unit operator, so they essentially do nothing, and you get x times x prime. But then by normalization of x eigenvectors x, this is d4 x minus x prime. So you have a double integral over d4x prime times this operator acting on this and x minus x prime. And integrate over x prime, set x prime equals to x, therefore then this object will look familiar. If you make an integration by parts, then of course this is the standard kinetic energy term for a real scalar field. So it is d mu phi minus n squared phi squared plus I epsilon phi squared. Okay? So I have written something familiar in some unfamiliar form, or maybe unfamiliar form. But then, having done this, the result of the integration is immediately obvious. Because our aim was to evaluate the integral z0j. We have to put here components. In the finite dimension case, I wrote d phi p and then product over p's. No? Here I should do the same thing. The product is over space points, if you like. And exponential of I, let me shorten the notation and write this as I0 of phi plus I'm writing in terms of components now, where I0 is what we obtained there, d4x phi minus d squared minus n squared plus I epsilon times phi. This exponent is precisely what we had before, so you need to create some space. In other words, we are considering the same integral and we know what the result is. The result of this integral is exponential of minus I over 2 j d inverse j. Now we have to find out what that object is in this notation in terms of components. Okay? Questions? So now we reach from one dimension to infinite dimensions. Let us see what does this object mean in the present case. In the case of one dimension thing, this was just inverse of a number. In the case of finite dimension vector space, it was the inverse of a matrix. Now we have the inverse of a differential operator. So we have to understand what the inverse of differential operator means. Okay? So to do that, we have to go back to the definition of inverse of an operator. The inverse of an operator, so the inverse, that's what you want to understand now. The inverse means an operator which when you multiply by d from both sides you get 1. That's why it's called inverse. Multiplication with the operator itself, it gives you 1. To find out what the matrix elements of this operator is, sandwich this relation between two basis vectors, x and x prime, and then insert a complete set of eigenstates here. So you put, for instance, d for y, x d y, y d inverse x prime equals to, this is of course we know what it is, it's d delta 4 x minus x prime. Okay? This one we already saw what it is. It is minus d squared minus m squared plus I epsilon times delta 4 of x minus 5. That's this part. Previously I had x prime here, now I have y. That's the only difference from what we had before. So this relation then is d for y minus d plus I epsilon times d for x minus 5 times y d inverse x equals to delta 4 of x minus x prime, d inverse x prime. Okay? Use the delta function to integrate over y. Therefore, the inverse of our operator is a function x d inverse x prime, which satisfies this differential equation. You have to solve this equation, find out what the function is. And you know how you solve these equations. What you do? You make a Fourier transform. So, we call x d inverse x prime d for k 2 pi to the power 4 d to the k exponential of minus I k dot x minus x prime, and plug it back here, dx squared acting here, it will bring minus k squared. There is a minus sign here, it will become plus k squared, and then the rest is trivial. K squared minus m squared plus I epsilon times d to the k becomes, if you do the Fourier transform of this, what do you get? The Fourier transform of delta 4? 1. So d to the k is 1 over k squared minus m squared plus I epsilon. So we know what this is. So we have x d inverse x prime equals to d for k over 2 pi to the power of 4, 1 over k squared minus m squared plus I epsilon exponential of minus I k dot x minus x prime. The object of interest for us, of course, is here, that fellow there. So we have minus I over 2 j d inverse j minus I over 2 d for x, d for x prime, j x, x d inverse x prime, x prime j minus I over 2 d for x, d for x prime, that is jx. Let me give a name to this in order not to write this long expression. I'm going to call all this minus I times delta f x minus x prime. You see that depends on x minus x prime. F, of course, stands for Feynman, and in my normalization I put a minus I there. This is a definition. I can put whatever I like there. Okay? But I'm putting minus I because of the way that I like to write the Feynman propagator in these things. That is not universal. I mean, other people define Feynman propagator in a different way. Some people even have factors of 4 pi in this definition in momentum space. These are all valid definitions. It's just a matter of what you are used to. If you correctly keep the various factors in your calculation. So let me put that definition here because it's an important piece of, this is a very important object in everything that we are going to do. So it deserves to be put inside the box so that we don't forget it. I put this I there so that you can multiply both sides by I and write it so that's delta f. I will be consistent with this notation. Always use the propagator in this form, okay, for everything. So therefore, for this matrix element here, we can put minus I delta f x minus x prime times j of x prime. And as a result, our Gaussian, this is equation star. So equation star becomes exponential of, there is minus I over 2 here and minus I here, gives you minus 1/2 d for x, d for x prime, j of x delta Feynman, x minus x prime times j of x prime. This is a central result, an important result, because everything will boil down eventually to evaluating the derivatives of this Gaussian. This is a functional of j, and it's a Gaussian functional of j. Gaussian means that here we have 2 powers of j. The rest is j independent. The rest is a constant. It's just a well-known function, namely it's a function here. So you can write it explicitly what it is. Okay, you can do this k integration. I think you know how to do that. This k integration and write that function explicitly as function of x minus x prime. Okay? And it's a Gaussian functional. It's important that it's Gaussian because Gaussian functionals or Gaussian functions are very good objects. You can easily differentiate them, integrate them, you can do with them whatever you like. You cannot do that with every function, but with Gaussians you can do it. Any questions? Why are we calculating this? Now, here is the main question. Why am I going through trivialities? The first part, the one-dimensional, n-dimensional, is of course triviality. You already know that. This is not a triviality, despite the fact that it's a generalization of them, but it's an infinite dimensional generalization of them. So you shouldn't look down at it as also as a triviality. In fact, it's heart of perturbative calculation in quantum field theory. The reason why, the relevance to physics, why we are looking at these objects, why we are examining them, is to make a link to what I told you in the beginning. I told you that the most interesting objects in quantum field theory are endpoint functions. Now we would like to see how this object is related to endpoint functions of an operator. So far there is no operator, no field operator here. It's all, this phi is a classical variable. It's not the phi that enters into this integration. It's not a field operator, it's just a function, ordinary function. It commutes. Different phi's at different times commute with each other. Okay? Quantum field theory has to deal with, or has to do with, quantum field operators. Quantum field operators do not commute with each other. How are we going to link what we calculated to quantum field operators? To do that, we will introduce a new functional. So define z prime is 0 of j to be the vacuum expectation value of time order product of I times, maybe you can't see it there. So define z prime j vacuum expectation value of I times the integral over d4x j of x phi hat of x vacuum. Now phi hat is an operator, but it's a free field operator. Namely, it satisfies the free Klein-Gordon equation. It's a scalar field. You know how to solve this. You can write in terms of creation and annihilation operators, and if you like, calculate this. The important thing about this functional of j is that if you differentiate with respect to j and set j equal to 0, you will obtain the vacuum expectation value of the time order product of phi's. So if we take d by I times dj x1, d by I times dj xn of z prime j at j equal to 0, obviously every time that you differentiate with respect to j, you will bring down the factor of phi. There is an I there, and I am putting an I here. Therefore, those i's will cancel. After differentiation, I will set j equal to 0. The exponent will go away after differentiation. The only thing which will survive is the vacuum expectation value of phi hat x1 to phi hat xn vacuum. So if I know this functional of j, by differentiating it with respect to j, I can obtain the endpoint function for a free field. Okay? Interacting field will have a nonlinear term on the right-hand side. This has 0 on the right-hand side, so it's a free field. Any questions? So this definition is clear, especially this step. Okay? The claim is that this functional is the same as our z. So claim is that z prime of j equals to z of j. And this is a useful thing. Why? Because we know what z of j is as a functional of j. It's a Gaussian. So this relation is telling you that in order to obtain the endpoint function of a free Klein-Gordon field, all you need to do is just differentiate the Gaussian of j and set j equal to 0. at the end. Okay? So it tells you how to calculate these matrix elements for any n. That's the reason why this is useful. What we are doing. Of course, we will see that it's also useful in interacting field theory. We will again calculate the derivatives of a Gaussian to obtain the endpoint functions of an interactive field theory. Okay? Any questions? Okay, so let's prove this statement. There are two ways to prove it. One of them I'm going to explain on the blackboard, and the other one I have left as an exercise to you. So first of all, the exercise. Let me explain the exercise first, and then I will tell you how we can derive it from very elementary things also without solving an equation. Of course, you need to know Wick's theorem in order to be able to do that. So let me first give you the exercise. So the exercise is the following. Take this functional and calculate 1 over I ez prime 0j by ej of x. Okay? And then show that this functional satisfies the equation j of x times z prime 0 j. You have to prove this using the fact that this is a quantum field and its quantization requires equal time commutation relation. So you have to use canonical quantization of phi hat in order to prove it. That's the exercise. Okay? The exercise is asking you use canonical quantization to show that this is true. And in the second part of the exercise, you see that this is a Klein-Gordon equation for this function with some source on the right-hand side. So you have to use a Green's function method to solve this equation and show that the solution is this. Solution is this, and we know that in Z0 it is the Feynman propagator interest, and you have to prove that in the solution the correct Green's function is Feynman propagator. So the second part of the exercise is the first part, that you should show that that satisfies this equation. And in the second part of the exercise, the second part is asking that show the solution is z prime 0 j exponential of minus 1/2 j of x delta Feynman x minus x prime times j of x prime. Okay? That means you are asked to show that the correct Green's function to use it is in fact the Feynman Green's function, not retarded or advanced Green's function, for example. Okay? Is the exercise clear? Now, but since you all know Wick's theorem, I am going to use Wick's theorem without solving that equation to prove this identity. Okay? Now, we know the right-hand side, and the left-hand side we know the definition. So we have to show that the right-hand side and the left-hand side are the same objects. How are we going to do that? Let's first look at the right-hand side. So, the right-hand side star. We know that Z0j is exponential of minus 1/2 j of x delta f x minus x prime j of x prime. Expand the exponential. So this is exponential of ordinary objects. There is no operator or anything. And we know what's the expansion of an exponential. It is n from 0 to infinity, 1 over n factorial minus 1/2 to the power n and nth power of this object. Okay? Each element in the exponent has a double integral over x and x prime. Therefore, when I write the nth power of it, how many integrals there will be? 2n. So there will be, let me use the same notation as here. So I will write those integration variables as x1 to d4 x2n instead of x and x prime. Okay? For the uniformity of notation. And then we will have n power of j squared, that means jx1 to jx2n. So this will multiply jx1 to jx2n. Then we will have n powers of this propagator, the final propagator, between them. This is the expansion of an exponential. But since the exponent is complicated, so the expansion of it needs some explanation. Is the notation clear? So 1 over n factorial comes from the expansion of any exponential. The rest is just the nth power of what is in the exponent. Okay? Now, something happens in the integrand. What happens is that the j's are symmetric under the exchange of x1 to x2n. No matter in which permutation of these objects you take, it's the same thing. It's a product of functions, the same function. Okay? But the coefficient is not. If you interchange the x's in the arguments of delta, you will not get the same thing. You will get a different thing. Since we are multiplying by a symmetric combination of j's, obviously only the symmetric combination of these objects will contribute. The anti-symmetric contributions will give you 0. Therefore, we should symmetrize this to see what contributes. How do you symmetrize it? You just add to the same object here, open a bracket, add to it all the terms that you obtain by permuting all the x's in the arguments of deltas. How many times we will produce in that way? 2n factorial terms. If you add all the permutations of these things, with all permutations of x's, there are 2n factorial permutations. So you will have 2n factorial terms. If you just stop there and do nothing else, obviously the coefficient will be symmetric, but you will have changed the value of the integral. Because instead of one of them, you are adding 2n factorials of them. And each one of them make the same contribution. Simply you can go from one to the other by a simple change of integration variable. That object will not change, but by a simple change of integration variable, you can bring back any one of those 2n factorial forms to the original form. Okay? So in order to not to change the value of the integral, we need to do something. What should we do? Divide by 2n factorial. So add all the permutations and but then divide by 2 in factorial. Then we have not changed the value of integral. Because in each one of these extra terms, simply we can make a change of integration variable and bring it to the original form. However, by doing this, now the object inside is symmetric. Okay? The next step is that we have produced 2 n factorial objects inside here, but not all of them are independent, not all of them are different from each other. There are some terms that we are writing twice by doing permutations. For example, which object will reproduce itself by adding its permutation to this?
When you do permutation?
For example, you exchange x1 and x2. That's among those 2 permutations. If you change x1 with x2, delta f will not change. So you will write the same thing twice. Okay? How many of such possibilities there are? 2 to the power n number of them. Because you are exchanging the arguments of each one of them. And there are n factors of them. So there are 2n to the power n of them. Okay? So we have to divide. You can divide by 2 to the power n and write only one of those things. You don't write x1 minus x2 and x2 minus x1. That is one other part of it that goes away, let's say. But that's not all. There are some permutations which just interchange 2 deltas. They don't give you anything new. For example, take the permutation of x1 with x3, which is done here, and x2 with x4. All that permutation will do is just to put delta f x3 minus x4 times delta f x1 minus x2. It will not give you anything new. And how many of them there are? As many as the number of these objects permuted, n factorial of them. Okay? So there is a, what am I writing? I'm confusing myself. You have to, sorry, I have to multiply. You have to take one of them, I mean this to n factorial, we have to keep, this one we have to multiply, yeah. So this is what the original thing, and then we are writing one of them and multiplying it by the number of the terms. So n factorial, not dividing. So I'm just writing, there are 2 things, I'm writing one of them and multiplying by 2. Instead of 2, you have 2 to the power n of them. So I just write one of them and multiply by the number, and likewise for this. Clear? So the p-factor will simplify. Because there's an n factorial here, which will cancel that n factorial here. There is a 2 to the power n, which will cancel this 2 to the power n in the denominator. The minus sign, of course, will remain. And then there's one extra 1 over 2 n factorial, which will survive. Therefore, when you do all these things, the result here will be 1 over 2 n factorials minus 1 to the power n, and everything else goes away. P for x1, P for x2n, times j of x1 times j of x2n, times, now here, I shouldn't write 2 n factorial terms, but I should write the sum of the product of deltas, let me write delta of xi, xj, but only independent ones, independent permutations. That means the permutations which do not generate the same thing again. Okay? So the number of terms will be reduced. It will not be 2 n factorial, but it will be 2 n factorial divided by these numbers. The product of 2 to n times n factorial. Okay? Is this clear? The simple combinatorics. It may sound complicated, but it's not complicated. Now, this is the right-hand side of the equality that we want to show. Let's go to the left-hand side. Left-hand side is this. Okay? So this is the right-hand side of. So we want to prove that this is what we want to prove. And we call it star, and this is the right-hand side of star. In this part of the blackboard, we are going to write the left-hand side of a star. The left-hand side of a star we should evaluate from here. So again, we do the expansion in powers of j. Now, the first thing is that when you expand in powers of j, you produce terms which have odd number of phi's in them and terms which have even number of phi's in them. Okay? So when you expand them, you will produce terms in which the number of terms is odd, and plus terms with even number of phi's. This is of course 0. You see why? For example, if you write in terms of creation or annihilation operators, it's obviously 0, but you don't need to do that. I mean, it's 0 because the symmetry 5 to minus 5, for example. Okay? So it goes away, therefore the only thing which survives is the terms with even number of phi's. So that's the only ones that we have to consider. And to keep to my notation here, I will write it as so I to the 2n divided by 2n factorials, then integration over d4x1 d4x2n j of x1 j of x2n times time order product phi hat x1 phi hat x2n. Ground state. Okay? Here you don't need any symmetrization. This is symmetric with respect to exchange of all the arguments, x1 to x2n, but this is also symmetric, because on the time ordering product, everything commutes itself. So that is what it is, as such. You don't need any extra symmetrization. I to 2n, of course, is minus 1. So we can erase this and quietly put minus 1 there. To the n, sorry. So the coefficient here is exactly the coefficient here. Okay? The rest, if you apply Wick's theorem, you have to make all the contraction, pairwise contraction of these phi's. In Wick's theorem, you replace the time order product by pairwise contraction of operators times the normal order product of same operators. But since we are sandwiching everything between the vacuum states, the normal order product terms will give you 0. So the only thing which will survive is the term in which you contract all the operators. Okay? Contraction of a pair of operator gives you what? Feynman propagator. So you know this. This is a definition of Feynman propagator, actually. This is one definition of Feynman propagator. But this is probably the definition that you have seen. Okay? You have seen this definition, right? If you haven't, write them in terms of creation annihilation operators, calculate the left-hand side, and show that the result is the 4-dimensional integral that we wrote down, with the factor of I in it, with the I epsilon denominator, etc. So this is precisely what we wrote as a Fourier transform, with all the factors in the right place. This is the reason. Now, hopefully, my strange notation for the Gaussian integral becomes clear. The reason I had chosen that notation was precisely to make this matching without any extra effort. That thing is precisely this. So, coming back to here, we have to contract pairwise all the phi's. All of them should be contracted with each other. Therefore, you will produce the product of Feynman propagators. And the combinatorics of Fick's theorem tells you that what you will produce from here is precisely what we have here. That means you will have the sum of product of Feynman propagators, only independent permutations. You will not produce all 2n factorials of them, but precisely as many as here. 2n factorial divided by 2 to the power n times n factorial. That's the number of terms you will produce from there. Okay? So this completes the proof that this thing, let me erase this lower part and put it here. So, Fick's theorem implies that this is precisely the sum of the product of independent permutations of delta Feynman xi minus xj. So therefore, so this is then equal to z0j. Any questions? Okay, so now we have a nice result. Our nice result is that, in fact, I'm going to write this down and stop. So we started from a definition of z in terms of a functional integral. By the way, instead of writing this long thing, I will just put a d phi there and the bracket around it. By that we mean the measure of the functional integration. We showed that exponential of I am taking the factor of half from here and putting inside of the bracket. I had an I over 2 here, but now 1/2 of minus d squared minus m squared plus I epsilon. I have a 2j phi, that 1/2 coming here will make it j of x phi of x. This is precisely what I had before.
You're missing a phi.
There's a phi here. Yes, thank you. We proved that this is equal to exponential of minus 1/2 d for x, d for y, j of x delta Feynman x minus y, j of y. We also proved that it is the same thing as the vacuum expectation value of the time order product of exponential of d for x, j of x times the field operator phi hat of x. So there is a Gaussian functional integral. This is a functional integral. It's a Gaussian. It is given in terms of a Gaussian functional of j. It's also given in terms of the vacuum expectation value of a free Klein-Gordon field times j. exponential of that, the time order exponential of that object. And why is it useful? It's useful because if you take the derivatives of this functional, which is j, and set j equal to 0, you'll obtain the vacuum expectation value of the product of field operators. That will be equal to taking the derivative of this functional integral with respect to j, which is easy thing because it's a Gaussian, and then setting j equal to 0. Therefore, of course, for this trivial case, you will recover what we wrote here, that this object is given by the products. Okay, you will not discover anything new. But then we will see in the next lecture that when we consider interacting field theories, then this will give us all the Feynman graphs. You can generate all the Feynman graphs in this way. Okay? So this is the end of this lecture, and then I will now ask for questions if you have questions.